where we are going to see some variants of the shifted partial measure, which were really inspired by some of the results which pinpointed the limitations of the shifted partial measures. So let me begin with a couple of them limitations of the shifted partial measure, and we have already seen one. Actually, this slide shows nothing, so let's see something. Okay. So we have already seen one. So let me try to explain what that is, and that's exactly the FLMS paper which showed lower bound for iterated matrix multiplication results. So let me try to explain in a little more details why it's a limitation of the shifted partial measure. So one way one could have proved separation between VP and VNP using the shifted partial measure is either by improving the upper bound for the circuit or by a better depth reduction to this kind of circuits, right? If you have a better depth reduction, like to a circuit of this kind which size smaller than n to the d by t, then you are through, because we already have a lower bound of n to the d by t. Or if you can improve the upper bound here, then you are also through, because you get something better than n to the d by t, and you prove VP not equal to VNP. This paper actually shuts the door on both the avenues in one shot. Let's see why. Because, and the reason is quite simple, because the target polynomial here is IMM, and recall from that figure that IMM is a family that resides in polysized algebraic branching program, which is contained in polysized circuit, like VP, right? So the family itself, the target family is in VP. So let's do it one by one. Is it possible to do a better depth reduction? No, right? Because this already shows that it will take this size circuit. You can't do better than this, and this is a polynomial in VP. It shows by an example that this particular family will need this, whatever the depth reduction actually gave you a circuit of size this much, n to the order d by t. And this one with an example, it is showing that this much is necessary. So this avenue is closed, and by what I explained in the last talk, even the other avenue, like improving the upper bound, is closed. The reason being, if you could improve the upper bound, that will give you a better lower bound for IMM, because the circuit has got nothing to do with IMM. I mean, the analysis for the circuit. Yeah, it doesn't use anything other than IMM or Nizan-Wigderson. And that would give you a better lower bound here, but which we know that is not possible, because depth reduction gives you n to the order d by t. So this one result, it's quite interesting. Okay, so pictorially, this says this following, that IMM resides here, and it's hard for this kind of circuit, right? And let's see one more limitation, and that's another remarkable paper by Mrinal and Shubhangi, which shows it's not just IMM. There is a polynomial which is computed by a very small homogeneous depth 4 circuit. But if you try to restrict the bottom fan-in, it will take large size. And that's quite remarkable about this result. So it basically shows, I'll give you a slightly detailed statement in the next slide perhaps. It says that there is a polynomial computed by small homogeneous depth 4 circuit whose shifted partial derivative dimension is close to the optimum, period. Okay, so, and that really pins down the limitation of using shifted partial as it is, because it seems like if I now ask you questions of this kind, that how can I show a lower bound for homogeneous depth 4 circuit? It seems like using shifted partial as it is won't give you anything, because it is already as high as possible for a polynomial residing here. How can you separate this from this if the measure itself is not exploiting any weakness of the circuit? Right? Is the point clear? Okay. So, and it is basically these two papers which motivated us to define and explore some variants of the shifted partial measure, which might be able to exploit some weakness of the circuits here, especially homogeneous depth 4 circuits. Okay, so let's time for some variants. Before that, let me give you the statement of Mrinal and Shubhangi's paper in a little more details. It says that there is an explicit family of polynomials in n variables computable by polysized homogeneous depth 4 formulas. But for a large range of t, that polynomial takes large homogeneous depth 4 formula with bottom fan-in bounded by t. And that largeness is as high as n to the d by t. So you can as well conclude from here that for this Fn, shifted partial dimension is very close to the optimum, and that's why you got this lower bound, n to the d by t. Yeah. So pictorially, it's this, that this homogeneous, it's a clear separation between homogeneous depth 4 formulas and homogeneous depth 4 formulas with bounded bottom fanning for a large range of t, as you can see. Right, so this I already mentioned, that shifted partial of this polynomial is close to the optimum possible. At the same time, it tells you something. Because of this, you know that one could have tried to reduce a general homogeneous depth 4 circuit to a homogeneous depth 4 circuit with small bottom fan-in without incurring too much of loss. And since you have already proved a lower bound for this, that could have given you a lower bound for this. But this paper shuts that avenue down. It says that you cannot actually have any efficient direct reduction from homogeneous depth 4 circuit to homogeneous depth 4 circuit with small bottom fanning, right? Right. So, and this is the starting point of our variant of shifted partial. And what we asked is this question, that can we somehow bypass this direct reduction by and still reduce homogeneous depth 4 circuit to homogeneous depth 4 circuit with small bottom fanning. And what do I mean by this? I mean exactly this. It is conceivable that you start with a homogeneous depth 3 circuit, and that homogeneous depth 3 circuit looks like a circuit, a homogeneous depth 4 circuit with bounded bottom fan-in, bounded by T, plus some junk part, some junk polynomial, some junk circuit. It's not exactly this, but it has this junk part. And why does such a thing help? Because the junk part could have complexity enormous with respect to a measure. But now suppose you also have a measure which is subadditive and which somehow kills off the junk part. Then what you get is that the measure applied on the circuit, you want an upper bound, right? You want to show that the measure applied on a homogeneous depth 4 circuit is small. So you can show that using the measure applied on a depth 4 circuit with bottom fan-in bounded by T, although C is not exactly computing CT, right? Or CT is not exactly computing C, right? So you allows a little bit of junk, but now you take hold of take advantage of the measure that you have and use the measure to kill off the junk part, so that the upper bound on CT still serves as an upper bound for C, right? So that's a very high level idea, but does it work, right? So let's see whether it works or not. Oops, several things are not appearing here. So let's see whether it works or not with an example. So let's see this example. Back to this classical Nisan-Wigderson homogeneous depth 3 circuit, right? Forget depth 4 for the moment. It looks like this, right? It's a sum of products of D linear polynomials. All of them are homogeneous, right? And look at the hard polynomial. The hard polynomial is IMM, let's say. It has layers. And out of these D layers, take half the layers, alternating, right? Half alternating layers. So these are the blue layers. So exactly half of them, or roughly, it's like d minus 1 by 2. Assume everything integer here. We are going to derive only with respect to variables appearing in the blue layers, right? Okay, now if we do that, we get that the partial derivative dimension, K is like this. The partial derivative dimension of IMM is greater than the width power 2K. Why? Because look at the number of Y variables here. It is W square, right? So I'm picking one Y here, one Y here, one Y here, one Y here, one Y here. And the moment you pick these Ys and derive, what you get is basically a monomial. And this monomial is unique for different derivatives. You take a derivative, you get a unique monomial. You take another derivative, you get some other monomial. So the dimension of the space spanned by the partial derivatives of IMM would be exactly the number of derivatives, because each derivative is giving rise to a unique monomial. And that's why it's W square whole power K, right? Okay. On the other hand, the partial derivative dimension of the circuit, we know, we have already seen this, that because it is subadditive, per term, when I take kth order derivative, it's at most d choose k. You can choose k of the linear forms out of the d linear forms, right? And this gives this, which automatically gives you a lower bound. Good. Yeah. So it's a little bit of repetition with the hard polynomial being IMM, because I'm going to use this later on. Right. So what's new? Nothing new. Now let's change the model to get something new. And the model now is, I changed the linear form. I replaced the linear forms by sums of univariates. We saw something similar in yesterday. So a linear form itself is a sum of univariates, right? But degree 1. But I change this. I make it slightly general and make it sum of univariates and d of them. Yeah, I call this, for at least for this talk, Srikanth's model, because Srikanth raised this question and that was the starting point of this work. So how can I prove a lower bound here? Can I use partial derivatives here straight away and do something? Let's see. Let's apply partial derivatives and see. No, but we are hit right at the onset. Partial derivatives applied on a measure can be as high as possible. Here is an example. Let's say all the q's are same. Look at one term. All the q's are same and they are exactly this. x1 square plus x2 square to xn whole square. If you take partial derivative, the moment you take derivative with respect to x1 will come out. And you get q to the x1 times q to the d minus 1. Moment you take derivative with respect to x2 will come out. And you get x1, x2 times q to the d minus 2. Right? So every derivative will leave its unique signature in front of q to the d minus k. So that space spanned by the derivatives, the partial derivatives, kth order partial derivatives, would be exactly the number of monomials of degree k in n variables, multilinear monomials. Right? Is this clear that why it is as high as this, n choose k? So it is as high as n choose k, you can't do anything. So the circuit itself is bad. So let's see now how I can use this kind of indirect reduction from this kind of circuit to homogeneous depth 3 circuit. And it would be an indirect reduction. Why? It's something very straightforward. You replace qij, you first think of qij, you split it up into the affine form, the linear part, and the rest. You keep the linear part here and keep the rest here. The rest is such that each and every variable will have degree greater than or equal to 2, right? Because the linear part is already absorbed. And then you replace, then you replace the qi's by this li's plus ji's. You multiply them. If you multiply everything out, what you get C to be a good part, which is like homogeneous depth 3, which is quite good, and a junk part. But I know something about junk part. The junk part was made up of these JIJs, right? And these JIJs are such, where did it go? Yeah, these JIJs are such that every variable here has power greater than or equal to 2, which means that every monomial here in the junk part will have a variable with degree greater than or equal to 2. Right? Is this part clear? That in this junk part? Now, so let's pause here for a moment. So this is how we split it up. And now I want to define a measure which can kill this junk part off. And this junk part is non-multilinear. Every monomial here will have a variable with degree greater than 2. So it's totally non-multilinear. Why not just use a simple projection which just looks at multilinear monomials, right? It sounds like in theory, intuitively it sounds fine, but it doesn't always work. The reason being is that if you recall the depth reduction to depth 3, we were going to very high formal degrees of depth 3 circuit, and it surely helps. There you surely have some kind of very magical cancellations happening to give you a polynomial of a very low degree. So going to very high degree will help. So as such, if I just restrict to low degree or multilinear monomials, it should not help. But the reason it helps here is because we are looking at homogeneous circuits. There the formal degree itself is small. Yeah, so that's the point. That since the formal degree itself is small, that's why you could define a measure and kill off this part and deal with this low degree part, which you would still be fine. Okay, so let's do this concretely. So let's define a projection map where S is a subset of 1 through n is the number of variables, which takes a polynomial and restricts it to just its multilinear monomials. And after restricting to just the multilinear monomials, it sets all the x variables inside S to 0. I should have said that, yeah, I'm identifying a variable with its index here. That's all. Okay? So every variable x1 through xn I'm identifying with 1 through n. That's all. Okay? So now let's try to incorporate this projection map into the partial derivative measure and see what happens. So I define a projected partial derivatives with respect to two parameters now, the set S and k, the order of the derivative, like this. You derive with respect to variables in S, k times, then you project only to the multilinear part and set all the variables in S to 0. The reason it is subadditive is because S is fixed. S is a fixed, predetermined set. I'm going to tell you what S is. Yeah? Okay. Now let's see what happens to the circuit. Because it is subadditive, I apply the measure, it gets split into these two terms. Now notice that this second term goes to 0. Why? Now the second term, every monomial has at least one variable with degree 2 or more. Right? And I'm applying multilinear derivatives. Either the derivative has a variable which coincides with x squared, let's say, in the monomial, yeah, or it doesn't. Let's do the easier case first. Suppose I'm deriving with a monomial and none of this monomial, and none of these variables in the monomial is that x squared variable in the monomial in C-junc. In which case the derivative will keep x squared untouched in C-junc, but the multilinear projection will kill it off. On the other hand, suppose C-junc has a monomial which has x squared and x belongs to the set S, because I'm only deriving with respect to S variables. Right? So if it does, then it will only derive once and then set all the x variables to 0. If I only derive x squared once, I'll still have x left, and then it will set x to 0 because x belongs to S. Right? So in either case, whether it belongs to S or not, this measure kills this C-junc part. And what we have, although you see that C is not equal to the homogeneous depth-free circuit, right? So which means that despite the fact that C is not being exactly computed by this, I can use an upper bound for this to get an upper bound for C. Right? And getting an upper bound for this is exactly like before. You just apply the partial derivative measure and it will touch k of them at most, and then set everything in S to 0, and S is a fixed fit. So that's why it works. You can take it as a short exercise that it's just exactly like this. And not only this, even for the Hart polynomial. Even for the Hart polynomial, it remains exactly the same. And this is quite easy to see. Let's take your S to be the S which we considered before. The set of blue variables here. Yeah? Now, IMM is such, if you take a derivative from with respect to a variable here, then after taking the derivative, the monomial that you are left with, it has no variable from the blue layers. And you are setting the blue layers to 0. So nothing happens to IMM, even after taking derivative. Is this point clear? So, and it's because of this that the derivatives are S-free, that the dimension of the partial derivative of IMM remains the same, even if you apply a projection map. The projection does not have any effect on the Hart polynomial. You use the projection to weaken the circuit. Yeah? Okay. So, right. So what you get from here is that circuit, this circuit C, which is a little general form of a homogeneous depth-free circuit, computing IMM, will have size W to the D, roughly. Okay, good. What did we learn, actually? Just to summarize, if you haven't followed anything, it's perfectly fine. The take-home message is just this, that what we did was, when we replaced a variable by a univariate, we had high-degree terms, right? And we wanted to kill off these high-degree terms. And the way to kill it off is to just restrict your attention to those monomials whose individual degrees are small. And that's exactly what we did by introducing this projection map. We just projected to just the multilinear monomials part. So this was just an example that how to go from a low, sorry, it's a typo here. Shama, I think there's something wrong here. I think it's a typo here. Oops, it looks pretty bad. Okay, so yeah, forget everything. So yeah, so now it comes right. See, so every monomial in Qij has support at most 1, right? But you wanted to get to degree at most 1, and that's why you introduced projection, to go to degree at most 1. Okay, so right. So forget the top part. Let's focus on the bottom part. Yeah. So, but to do this for a homogeneous depth force circuit, that was the target, right? You want to reduce a homogeneous depth force circuit to a homogeneous depth force circuit with low support, right? Once you come to a low support, then you can hope to apply a projection to go to low degree by killing off all monomials which has a variable with high degree, right? And that, yeah, projection maps only helps you to go from low support to low degree. Right, so let's do this. How to go first, a reduction from a homogeneous depth force circuit to a homogeneous depth force with low support. Okay. And the way to do it is fairly obvious. You use random restriction, which was used by Ranras before in a very subtle way, but we use it in a very naive way. Okay, so just set every variable to 0 with some high probability. Retain it with some small probability, independently at random. Now, you can intuitively imagine if a monomial in this circuit has a large support, under random restriction, it will become 0, right? So only small support monomials will survive. Now, the intuition here being, so right, I'll give the intuition, but so you apply the random, let's call the random restriction map sigma r. You apply the sigma r, it just distributes across all the Qij's, and it looks like this. And let's do the analysis a little more in details, that why we hope that the circuit that we are going to be left with will have low support. So let's say S is the total number of monomials in all Qij's. Okay, sometimes we call it the total sparsity of the circuit. Yeah, I just count all the monomials appearing in all Qij's over all I and j. Now, what is the probability that there is a monomial whose support is larger than t? Right? So you apply union bound. Take any monomial. If its support is larger than t, its survival probability is n to the minus epsilon t, because I'm retaining variable with probability n to the minus epsilon. Yeah, I'm setting it to 0 with probability 1 minus n to the minus epsilon. So which means if S is not too large, then there won't be any monomial with support larger than t. Right? Just apply union bound, and if S is greater than this, then only then only the process can fail. Then only random restriction can fail. Okay. So the summary is this, that unless the circuit itself is large, which means its total sparsity is large, random restriction will weaken a homogeneous depth force circuit to a homogeneous depth 4 with small support. I'm using curly braces now to denote small support instead of square braces. Okay. On the other hand, if I really choose a very, very hard polynomial, I do expect that it will retain its hardness even under random restriction, because I'm really leaving a lot of variables still intact. Yeah, although I'm killing off many, I'm still leaving many variables intact. So can this be used? Yeah, so this intuition. That on one hand, I'm weakening the circuit, on the other hand, I'm not weakening the hard polynomial that much, hopefully. So I'll just rephrase what Amit is saying. So what we showed, now the random restriction, unless the sparsity of the circuit is large, it will weaken the circuit, right? So suppose you could prove, let's say, you could prove a top fan-in lower bound of the best possible for this kind of circuit. We already did it, but for square braces, not curly braces, when the bottom fan-in is small, not bottom support, right? By the way, so I hope the word support is clear to everyone. Okay, so as a lower bound, what do I get? I get the two things. It's a minimum of two quantities. If random restriction fails, then the circuit is anyway large. How large? We just saw. that sparsity, unless sparsity is greater than n to the epsilon by 2t, then random restriction will succeed. So if it fails, I get this lower bound, and if it doesn't fail, I get a top-finite lower bound. Right? So it would be the minimum of these two quantities that I'm going to get. And if you choose your t appropriately, which is like root d, to make both the terms equal, what you get is a size lower bound is on this. Either the circuit is anyway large, so I have nothing to prove, or if it is small, then I prove a lower bound on the top finite. That's what this is saying. Okay? So, good. So now all that remains is to prove a top finite lower bound of this, of n to the d by t, but for homogeneous depth 4 circuit with small support instead of small finite. We know how to do it for small bottom degree, but not bottom support. Okay. Okay, so the next step would be to introduce projection to reduce this small support case to small degree. Okay, and this we know intuitively. We saw an example how to do it. You just apply multilinear projection and you would be done. Right? So we're going to do exactly that. And in a far simpler way. Yeah, we're just going to use this map pi, which has no s as a subscript or anything. That was the example was more complicated than the actual case. Okay, so pi of g is the sum of multilinear monomials in G. Right? That's the map. And notice that if you apply pi on G, and if G has support less than t, then pi of G will have degree less than t. Right? That's all. And now you augment the shifted partial measure by introducing a projection right in outside. Okay. So what does this mean? I take derivatives, then I shift. Yeah, I will get a polynomial, and then I retain only the multilinear monomials of that polynomial. Yeah, that is my polynomial, and you look at all such polynomials and the space spanned by these polynomials, and look at its dimension. Because I'm using a multilinear projection, it does not make sense to shift by a monomial which is not multilinear, right? Because if I multiply by a monomial which is not multilinear, then pi will kill the whole thing off. Because pi retains only multilinear monomials, right? So that's why I will just shift it with only multilinear monomials of degree t. Okay, it turns out that this is again subadditive, quite nice. But let's see how large can the projected shifted partial derivative measure be. It's a very naive quantity. Let's look at how many polynomials are there in this set. The number of multilinear shifts is n choose L, and the number of derivatives, because they are multilinear derivatives, they are n choose k. So you have these many polynomials in the whole set. And every polynomial has degree at most L plus d minus k, because we are restricting only to multilinear monomials, right? Here, if I start with a multilinear f, the degree will drop to d minus k, then it will increase to L plus d minus k. And how many monomials are there? Multilinear monomials in n variables of degree L plus d minus k, these many. So the projected shifted partial derivative of f would be a minimum of these two quantities. So initially we had something else for shifted partial. We have something similar here, but it's changed slightly. Okay. Now, as usual, you assume that we have such an f. Yeah. So that's not a big deal. Yeah, that was actually a big deal in the paper, but not for the talk. Okay. So in this talk, let's assume that we have an f which has the maximum projected shifted partial. And let's complete this task of reducing a homogeneous depth 4 circuit with low bottom support to a homogeneous depth 4 circuit with low degree, bottom degree. Okay, so let's start with such a circuit which has low bottom support. Yeah, and you do as before. You split every Qij into a good one, which has actually degree small, and the bad one, which has high degree. How do I split it up? I restrict this Q prime to monomials where every variable has degree 2 or less. Now you could ask me like, why are you retaining degree 2 things? You could have said like, retain only the multilinear monomials. We'll see. The point is like I'll have to derive next, and then the projection comes. If I want to kill a variable, the derivative might reduce the degree 2 or degree 1 from degree 2 to degree 1, and the projection won't kill anything, right? So if I want to kill, then I have to focus on monomials where there is at least one variable with degree 3 or more. In there, if you derive once, then the degree will come down to 2 because it's a multilinear derivative. And then the projection will kill it off. Yeah? So that's why we split it like this. Yeah, this junk part is such that every monomial has a variable of degree 3 or more. Okay, good. So now you focus on a term, you multiply these things, then these q primes, the good parts gets multiplied, and each of them has small degree, and you have the junk part here, where every monomial has a variable of degree 3 or more. Yeah? Now you apply the measure, projected shifted partial derivative, because it's subadditive, it gets applied on both. Yeah? And now notice that this part is 0. Why? Well, you just derived once, and then you shifted, and then you took a projection. Yeah? And every monomial, just focus on one monomial there. It got derived, it has a variable of degree 3 or more. It got derived, so the degree 3 part might have come down to 2, then there was shift, which can only increase the degree, and then there was a multilinear projection. So each and every monomial here will get killed. Right? So once again, it is not a direct reduction, but it's some kind of an indirect reduction where every term which had low support got reduced to a term which has low degree at most 2t. And now this behavior of this is pretty much like the shifted partial derivative. Yeah, so this would be small, so you need not pay too much attention, but just for completeness, let me just do it once. So let's see how a low degree term behaves. Yeah. Now assume that all the q's have degree at most 2t. Right? I'll just do roughly the same argument as before. So when you derive k times, at most k of the q's are touched by the derivative, right? A q might be touched twice, but just for simplicity, assume that it's touched once. Yeah, so you just multiply all the touched q's and make it these green boxes. And this green box will have degree at most 2kt, right? Because each of them has degree at most 2t, and there are k of them. Right? So every derivative looks like this. Now you shift. You shift by a monomial of degree L. So in this green part, you absorb the u monomial. So the degree goes up by an additive factor of L from 2kt, right? And now you apply the projection. Now when you apply the projection, if you look at this green parts, all the multilinear monomials will get killed. What would be left in here would be all the non-multilinear monomials would be killed. What would be left would be only multilinear monomials of degree at most L plus 2kt, right? Because the projection will kill everything off. So now see that every such term can be expressed as sum of these terms, where you can assume that these are multilinear monomials of degree at most L plus 2kt. Every such polynomial here. Naturally, the projected shifted partial derivative of a circuit, because of subadditivity, it is S times the projected shifted partial of each and every term. And every term, you see it has a q part here, and how many such q parts can be there? M choose k, because it is coming from this how many green q's are touched. Okay? And this part is coming from the green box. How many monomials are there of degree at most L plus 2kt? Multilinear monomials in n variables. Right? So this gives an upper bound. Right? So yeah, so we got an upper bound, cool. Right? And because everything is homogeneous again, I can replace m by d by 2t. Because individually everything has degree, let's say 2t, and overall degree is d, so roughly there are d by 2t many terms. So the upper bound looks roughly like this. Good. Overall, again we come down to this very strange looking ratio. This is the best possible, as I said, and this is the upper bound. Yeah? And this is the top and lower bound that you can possibly get for a homogeneous depth 4 with low bottom support. Right, it turns out, I'm not going to go into the details, it turns out that once again there is a nice choice of L which comes from this diagram of finding the sweet spot. And K, you can easily see that I have to choose KT to be less than D, otherwise this term will be really small compared to this term. So the choice of K becomes obvious once you stare at this ratio, that it has to be some delta times D by T. And then fix that K and then do that calculation where to find the sweet spot, And you get a L prime, and once you plug in that L prime, you get once again this n to the d by t. Okay, so now we are done, and what remains is that showing that there exists an explicit polynomial with high projected shifted partial, and this was exactly what was shown in this paper with Neeraj and Nutan and Srikanth, and it shows actually that the projected shifted partial of the Nizan-Wigderson is actually quite close to the best possible. And once again, you lose a poly factor, not more. Yeah, with some range of parameters. That's all. Yeah, and you plug in there, you get your bound. That's all. Okay, so I won't go into the technicalities, but let me give you a very, very high-level view as to why the proof is different this time, and it became different this time. Yeah. Yeah, I'll come to it. IMM, yeah, I think Mrinal and Shubhangi showed that even IMM has projected shifted partial, which is close, but you don't lose a poly factor, you lose a little more, an exponential factor, but that is still nothing compared to, for example, if you lose a 1 by 2 to the d by t factor, because the ratio is n to the d by t, 2 to the d by t does not affect the final lower bound. Okay?
What happens to random restrictions? This is after random restriction?
This is, yeah, even after random restriction. Yeah, you know. Let me take that back. After random restriction, you lose an exponential factor. You lose a 2 to the d by t here.
But you need to show it after random restriction.
Right, but this is for only homogeneous just with bounded bottom support.
Oh, I see.
Right? Yeah. So right. So random restriction, we need that. We need random restriction. But if you apply random restriction and then use the measure, you lose a little more. But I'm just saying that if you just apply the measure on Nizan-Wigderson, then the loss is not much. But if you do random restriction, naturally it would be less because you are killing off a lot of variables. So there would be a much more loss compared to what were the original n variables. Right? So, okay. So, fine.
Just one comment about the random restriction. The random restriction doesn't, one simple fix for it is you just replace each variable by a large linear polynomial in disjoint sets of variables, on disjoint sets of variables. So you can do a probabilistic analysis, so even if you reduce it, every guy in any such block will be left.
Right.
So you can always project back to this and prove your own.
That's right. Yeah.
So
That's a simpler way of saying this. Yeah, that's correct. Yeah. Okay. So let me just give you the high-level view. And okay, overall, what you get is that Nizan-Wigderson polynomial, if any homogeneous depth 4 circuit computing Nizan-Wigderson polynomial will have size at least this, n to the root d. Okay. Right. So why is the analysis a bit different? So let me just briefly sketch. What we want to analyze is rank of this matrix. What is this matrix? You write down all the polynomials, all the n choose k times n choose l polynomials, whatever you get by deriving and then shifting. Write down all these polynomials, they're coefficients. Yeah, these would be 0, 1 coefficients. And how many columns are there? Exactly the number of exactly the number of multilinear monomials, right? Because these are all polynomials in n variables, and they're multilinear and degree at most l plus d minus degree exactly l plus d minus k. Okay. The point was earlier, as I was mentioning towards the end of the first talk, that once you derive a Nizan-Wigderson, the derivative became a monomial. Then you shift by a monomial, it's again a monomial. So what you reduce the problem to is counting the number of distinct monomials in this overall set that you're getting. That would be a lower bound on the dimension. But here, because the choices of the parameters had to be different here, I just hid everything. The choice of the parameters, as you see, I replaced k by r here. Earlier it was k. And here I replaced it by r, and r is like close to d. So here the overlap is not that low. It is still high. So what you will get here after deriving is not a monomial. It will still be a polynomial. Because derivative order is k. K is much smaller than d. And the overlap can be order d. Right? So that was the problem. So what you get here are like not a diagonal kind of matrix, which would have been the case if all the derivatives had been monomials, but just general polynomials. But what we found is that because of this disjointness properties of monomials, this matrix has a very nice structure. The columns of the matrix are nearly orthogonal to each other. This is a 0-1 matrix. Yeah, they are nearly orthogonal to each other, and I won't quantify what that near thing is. Which means if you look at this matrix, which is M transpose times M, if the columns are orthogonal, let's say, what you will get B to be a diagonal matrix, right? And if they're nearly orthogonal, you get B to be a diagonally dominant symmetric matrix, right? And notice that if you prove a rank lower bound on B, that will imply a rank lower bound for M. And this is over any field. Yeah. So what we reduce the problem of showing a rank lower bound on M to a rank lower bound on to proving a rank lower bound on B using this nearly orthogonal structure. And you're right. You're right. But what I'm saying is like this inference holds over any field. Yeah. Okay. So right. So and now we have a very nice lemma. It's due to Noga Alon, which gives us a way to lower bound rank of a B using its traces. Yeah. And this is exactly what we used, and it found that the traces of this matrix B is tractable, and we can actually find good exact quantities capturing these traces. One plug in these traces and you get a nice lower bound here. Okay, so let me tell you before going forward that in a subsequent work, actually Mrinal and Shubhangi also analyzed something similar, but they did not take this route. If you take this route, this thing holds only over real numbers. The proof is a straightforward proof you can take as an exercise using eigenvalues. Symmetric matrices will have real eigenvalues. That's why it's a very straightforward proof, 2-line. And this holds over only reals, and you can make it work over any characteristic zero field. Right? So that's why our proof, our lower bound, holds only over fields of characteristic zero. But later on, Mrinal and Shubhangi actually analyzed something similar, and what they did was a more direct approach. They found a nice large triangular matrix inside this. If you find a nice large triangular submatrix of this matrix, that itself will serve as a lower bound for this, and that's how they proved it for IMM, and that too over any field. So, okay, so I'll perhaps mention that once again. But in summary, what we showed is that this Nizan-Wigderson polynomial, which resides in V and P, I did not tell you why it resides in V and P, but again, it's not hard to see. That polynomial is hard for homogeneous depth circuits. And later on, as I was mentioning, Kumar and Saraf showed that you can actually take the hard polynomial to be IMM and show that it's hard for homogeneous depth circuits over any field. Okay? How much time do I have now? Five minutes. Okay. Okay. So let's see. So the question is whether now one can make the lower bound stronger and show that ABP is hard for homogeneous formulas. That's open. Now, one related question is a question in the non-commutative world, which is also open to my knowledge, separating non-commutative ABP versus non-commutative formulas. So the non-commutative term was probably not introduced in the tutorials, but it's basically the same arithmetic circuit, but this time you assume that variables don't commute with each other. It's a model used to capture matrix multiplication or computations using matrices, where the non-commutative model is quite natural, right? Because matrices usually won't commute with each other. And there, I don't need anything more than this picture about non-commutativity. So it turns out that the separation is also open. But one nice thing to observe is that one can actually prove something in the commutative world to prove something in the non-commutative world. And that's the following. Now, if you can show that IMM is hard for not homogeneous formula, but multilinear formulas, then that will give you a separation between ABP and formulas in the non-commutative world. Now, why M stands for multilinear as usual? Why am I hopeful here? Because we know of superpolynomial lower bounds for multilinear formulas. where we depth reduced it to a special kind of depth force circuit, which is like a log product. Yeah, but there the hard polynomial was determinate. So it turns out that this is open, that we do not know how to do it with IMM as the hard polynomial. Yeah, a related work is a work by Divir, Malod, Perifel, and Yehudeov, who actually separated multilinear ABP from multilinear formulas, but then again, the hard polynomial was not IMM. Yeah, and with that choice of a hard polynomial, you cannot infer separation between formulas and ABPs in the non-commutative world. Okay, so the natural question is that to begin, at least can I show that IMM is hard for multilinear depth 4 formulas? Yeah, but the goal here is to show that IMM is hard for multilinear formulas. It turns out this we can show. Yeah, I'll very briefly go through it. But just let me tell you the issue. Why did projected shifted partial not work straight away in this case? The problem is you are dealing with a multilinear circuit. The reason you used projection was to weaken the circuit, to find some weakness of the circuit, go from high degree to low individual degree. But here to begin with, the circuit is multilinear. Even if you apply a multilinear projection on a multilinear circuit, it's not straight away clear what will happen. Yeah, so perhaps you need something else here. So, and it turns out that a different variant of shifted partial measure helps here in actually giving the lower bound. So I won't give you the proof, but let me give you just the history of this. That Ras proved that determinant is hard for multilinear formulas. What we want is IMM is hard for multilinear formulas. And the reason the determinant lower bound does not give an IMM lower bound for multilinear formulas is because the reduction, and this is kind of strange, you see, both are residing inside ABP and both are complete for ABPs. So you can reduce one to the other and vice versa. It turns out that the reduction from determinant to IMM, it does not obey multilinearity. But the other way, it does. So if, for example, if you prove a lower bound with IMM, that will immediately imply a lower bound for determinant, but not vice versa, against multilinear formulas. Okay? So, right. So still history, and this was covered by Ram Prasad. And the way they did it, they showed Raz Yehudev, and another paper which I missed here is by Raz Pilka and Yehudev for multilinear circuits, and various very interesting and compelling results and separations for multilinear formulas and circuits. They use this measure which uses partition of variables, and Ramprasad's talked about it, how it by randomly partitioning variables into roughly equal chunks, you look at something called the partial derivative matrix and its rank. But if you were not present in his talk, just take this as the simplest example. This is the measure. Like you take a random partition, you take the variables, partition it randomly into x and y, yeah, and then you take all possible derivatives with just the y variables, and after you take the derivatives, set the y variables to 0, and look at its dimension, the space spanned by. This is exactly the rank of the partial derivative matrix with x and y as the partition, right? So, and that was the starting point in our work. That can we somehow use shift, yeah, and augment it with this rank of the partial derivative measure in a nice way that works. And yeah, I won't go into the proof, and it turns out that I thought of only giving a short proof as to how it works for multilinear depth 3 circuit, but let me not go into the proof, but let me just skip a few slides and tell you that one crucial aspect of this new variant is that unlike the previous case where you were choosing you're partitioning the set of variables in two roughly equal parts, here we deliberately partition it deterministically, not randomly. Deterministically, we partition it into unequal chunks, hugely unequal, not by a constant factor or anything. You can see, like, yeah, forget everything. You can see that we are partitioning here, like, there's a factor of W here. So hugely unequal chunks, and somehow that turns out to be quite crucial. Yeah, I can give you the details, but I think I'm running out of time, so I'll perhaps skip these later slides and go straight away into the open problem section. Yeah, just a glimpse that this is how we augment the rank of the partial derivative measure with a shift and then look at its dimension. So let me just go away to, I'll end in 1 minute. Yeah. So a few problems which I find quite interesting at the moment. One is this, which I already mentioned, that prove that IMM is hard for multilinear formulas, and it looks doable to me because right now shifted partial measures have been incredibly successful in handling low depth circuits, and we know how to prove multilinear formula lower bound via low depth circuit using this log product kind of formulas, which is a sort of a special depth 4 circuit. Is it possible to use shift in a nice way so that you can apply it on log product kind of expressions and get a lower bound for IMM? It would be really nice. That would give a separation for in the non-commutative world. Okay, so another, I think the pressing question right now is to prove a lower bound for depth 3 circuits in general. And it's a bit embarrassing because we have so many models, and at depth 3, it's the first non-trivial model without any assumption. We don't have any super polynomial lower bound. The closest is this work with Neeraj, which shows that as long as the bottom fan-in of the depth 3 circuit is small, the bottom fan-in can be at most n. What we show is that if it is a little less than n, actually a lot less, because epsilon is something, but you can choose epsilon to be as close to 1 as possible. 1, if you can replace epsilon by 1, that would be general depth 3. Yeah? And for that, you get some nice lower bounds. See, the depth reduction to depth 3, the chasm at depth 3, is still not a sufficient reason as to why we are unable to prove lower bound, super polynomial lower bound for depth 3, because that was the case even for homogeneous depth 4 with bounded bottom fan-in. But there was a chasm even at homogeneous depth 4 with bounded bottom fan-in, and there we could successfully prove a lower bound, more than super polynomial. But here, it's not clear to me. Why not? I mean, so something must be really.
What is the lower bound degrade with epsilon?
You fix an epsilon, and then you get. I'll tell you offline how that's. It's not a complicated expression. Okay. So one suggestion which actually came to know from Ankit a long time back is to go via. Oops, forget everything here. So to go via homogeneous depth 5 circuit. He said something like, and this was known even from one of Spilka's result early on, and he also showed the similar kind of reduction. So the problem was that in a general depth 3 circuit, I don't have any control on the formal dB of the circuit. One way to get around is to reduce it to a depth 5 circuit, homogeneous depth 5. So, but you get homogeneity. Yeah. So if you can prove a strong lower bound for homogeneous depth 5 circuit, that will give a lower bound for homogeneous depth 3 circuit. And this does seem like a viable route, because actually we got this lower bound by actually proving a lower bound for homogeneous depth 5 circuit. Okay. The third problem is we proved a lower bound for homogeneous depth 4 circuits, but with polynomials like IMM because of Mrinal and Shubhangi. But it might as well be the case that the hard polynomial is just the elementary symmetric polynomial. Because if you remember from yesterday's talk, that elementary symmetric polynomial is hard for homogeneous depth 3. Is it also hard for homogeneous depth 4? Perhaps any homogeneous formula? It's possible. I mean, I'm inclined to believe that, but as a first step, one can try to prove the same lower bound for homogeneous depth 4, but with elementary symmetric polynomial as a hard polynomial.
But we can't expect n to the root d, right? We can expect 2 to the root d.
Yeah, that's true. That's true. That's true. Yeah. So he said like we can't expect like the best possible like n to the root d lower bound, but 2 to the root d perhaps, and that seems like the right one. But the problem that it doesn't work yet is because one can show very easily that the projected shifted partial measure, which worked for homogeneous depth 4, it's actually quite small for an elementary symmetric polynomial. And one can very easily show that. Not a big deal. Yeah.
So the depth is circuits for the elementary symmetric polynomials basically show that up to a polynomial factor, it's the same measure as a monomial.
Right.
Because
That's true.
shifts usually don't affect those measures, and then it's just the sum of n shifts.
That's true. That's true. But let me also add that if you recall that work by some FLMS, that they actually tried to show that the shifted partial of the symmetric polynomial is high. And that they could show only for a restricted range of D. Yeah, but It could be possible that the shifted partial is high, but then the problem is the shifted partial of the circuit itself is also high because of the result by Mrinal and Shubhangi, that shifted partial of homogeneous depth formulas are high. You want a measure which is high for this, but low for this. And that is something which I think we don't have yet.
This measure has to be high for a monomial, and it doesn't make sense in some way, right? It's like, right, but still, it's counterintuitive that the monomial will have high measure, and the circuit like that will have low measure, right?
But that measure should obey some property, right?
That argument, but then that intuition should also fail for bounded bottom tunnel depth fold.
Right.
But FLMS show that when D is very, very small,
Right.
they do prove a lower bound of n to the omega square root D. But you can't do that for a monarchy. I mean, it's a little subtle with
No,
parameters.
because of homogeneity, right?
Because of
Yeah,
homogeneity.
it's because of
Yeah.
homogeneity.
So it's only for low, when you go for high degrees, it's,
Yeah, high degree, but I don't know, maybe we can still reduce high degree to low degree by some.
No, but I guess
I don't know.
one catch here is that elementary symmetric polynomial is something with a huge partial derivative space, but the partial derivative matrix has small rank. And from the intuition of Shrikant's model, the projected shifted partials is something like it's like a partial derivative matrix analog of the vanilla partial derivatives, and that's one of the reasons why elementary symmetric polynomial just the rank crashes.
Okay, so I think in summary, it means that we need something new. So search for something. Okay, that's the takeaway message. Okay, the final problem I want to leave you. So in the recent past, a lot of lower bounds have been proved using this new polynomial family called the Nizan-Wigderson polynomial family. And right now we know nothing about it. Its exact, where does it belong exactly, apart from the fact that it belongs to VNP. The question is it VNP complete, or can you show with some nice assumption that it's unlikely that it's VNP complete? So so something we don't understand about the complexity, the exact complexity of Nizan-Wigderson polynomials. So might be worth investigating this. Yeah, thank you very much.